Alright, let's get straight to this. This video we're going to be talking about evaporators and its counterpart condensers. So pretty much all what an evaporator does is, let's draw a little evaporator. This is my little evap. We have some fluid in there. Let's just say it's H2O, doesn't really matter right now. And there is some heat going in. There's some Q which causes the H2O to go from a liquid to gas. That's pretty much all it does. So let's draw out the continuity equation. We have Q plus mass flow rate times enthalpy plus potential energy plus potential energy, so that was kinetic energy, equals work out plus mass flow rate times enthalpy out plus kinetic energy, then HV2. There we go. So what can we eliminate here? Well, like normal, I don't really care about potential energy or kinetic energy. They do matter, but not nearly as much as enthalpy. And then we have work. There's nothing moving here. All we're doing is holding like a pan over some flame, like a pot of water over a flame. There's nothing, no mechanical work being done. So all we really have is heat in plus mass flow rate times enthalpy in equals mass flow rate times enthalpy out. So heat transfer is mass flow rate times H2 minus H1. And that's it. So let's do a quick example problem. Let's keep with H2O. So we have some evaporator, and on the inlet state we have, this is H2O. We have a saturated liquid at 100 degrees Celsius, and coming out we have we know water is going to be at 200 degrees Celsius and 200 kilopascals. Now I want to know what's Q. Alright, so all we have to do is use the continuity equation and plug and chug. So we need enthalpy of state 2 and state 1. So we know it's a saturated liquid, so we can go up and we can look that up in the table. 100 degrees Celsius is more or less 99.6, so we can just assume that's going to be at 100 kPa, and the enthalpy there, so H1 equals 417.44 kilojoules per kilogram. And state 2 here, let's see, state 2, that's looking straight up in the table. The 200 degrees Celsius, 200 kilopascals, that's superheated gas. So let's H2, look that up in the book, and it's 2,870.46. I just want to make a quick note about the difference, the very big difference in scale between the inlet water, which is just liquid water, and the output water, which is steam and has a lot more heat, a lot more energy. So it has a significantly higher enthalpy here. Let's see, now we have everything we need to solve the problem except for the mass flow rate, which I forgot to give you, which is just going to be, for simplicity, mass flow rate is 1 kilogram per second. So, yeah, plug and chug. Q is going to equal 1 kilogram per second times 2,870.46 minus 417.44, and that's kilojoules per kilogram. And then we are left with, once you do the easy subtraction there, 2,453.02 kilojoules per second. And that's how an evaporator works. Now, I've never really talked about condensers. Just like the difference between a turbine and a compressor, the only difference is the direction of Q. So, if this was an this was a condenser going from this state to this state, it'd be the exact same problem, but Q would just be negative. That'd be the only difference. And then these two would flip, which would cause the negative sign for Q. Alright, and that's it.